And proceed.
Yeah, thank you, Dr. Divya. So, good afternoon, everyone, to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences. This is today will be the lecture number 25, the last lecture in the series. This series is jointly hosted by South Asian Meteorological Association SAMA and Savitribai Phule Pune University. Before we proceed for the lecture, which will be given by Professor C.A. Babu from CUSAT, I request Professor Tyagi sir, who is President SAMA, to please deliver the welcome address.
Thank you, Rohini, and I'm really very happy that this last lecture is being delivered by Professor C.A. Babu, who was the main initiator to conceive and plan this particular training program, important training program on atmospheric dynamics. Thank you, Professor Babu. You have also delivered earlier a couple of lectures for us. So overall, the series has been well received. It has been by I think participation of eminent meteorologists, practicing meteorologists, both from the academic as well as from the operational side. We had Dr. Datta, Somnath Datta from IMA delivering lectures, a series of lectures. Similarly, Professor Karipot from Pune University, you are there. So we had a good set of lecturers who covered this important topic. It is unlike many other topics on meteorology, is much more abstract, but all of you have made it simple. And the feedback which we had been receiving is positive, excellent. And since these lectures are available on YouTube, we are impressing upon the students who are not able to attend these lectures because of the time zone difference or other reasons, can go through these lectures and benefit. And also, our request to all our resource persons are there that they should be able to guide the students who would like to get their doubts clarified even after this lecture. So I once again thank you so much, and my also compliments to Rohini and its organizing team at Pune University and IITM from IITM, who have managed this 25 lecture series very well. And also the follow-up of this which is required is the abstract compilation and also the examinations which will be held. So these are the two more important events which I am sure Rohini and his team will take care of. So once again, welcome Professor Babu. Thank you so much. And all participants have a great time. We are touching 40. I'm sure we'll cross 50 marks by the time lecture starts. Thank you.
Thank you, sir. Yes,
Dr.
thank you, sir.
Tyagi and others of SAMA lecture series for your support and cooperation, and welcome to the participants to the lecture number 25 on mixing length theory, variation of wind in the surface layer and Ekman layer. Let me introduce planetary bound layer. First, planetary bound layer is the layer just above the surface in which the surface friction
Sorry,
forcing.
sir, still it is not shared. So kindly share your file.
Okay, just a moment. I thought it was shared. Yeah. Okay, I understand. Okay, no problem.
Also, since this is the fourth lecture on PBL, so maybe you can skip the introduction part of the PBL, right, Professor Babu?
Yeah. Can you see the presentation?
Yes, sir, we can.
Yeah. Okay.
Yeah.
Let me continue. Sorry for the interruption. And planetary bound layer is the layer just above the surface in which surface frictional force is dominant. The PBL can be subdivided into laminar sublayer, Prandtl layer, and spiral layer on the basis of features in the sublayers. As shown in the diagram, the laminar sublayer is very shallow layer. Its height is a few millimeters. Next is Prandtl layer. It is 50 meter to 100 meter. And in the Prandtl layer, the surface frictional force is one order larger than, or turbulent drag force is one order larger than pressure gradient force and Coriolis force. Next is Ekman spiral layer. So let me explain briefly the features of these three layers. Laminar sublayer is formed over a smooth surface with a thickness of a few millimeters. The flow in the laminar sublayer, the flow in this layer is laminar, and major exchange process is molecular diffusion. In a rough surface, laminar sublayer does not form. Rather, a turbulent layer known as Prandtl layer forms from the surface. For example, in an early morning ocean surface, the laminar sublayer need not form because of the smooth surface. On the other hand, in an early morning ocean surface, laminar sublayer forms. On the other hand, in the afternoon over a complex terrain, the laminar sublayer does not form because of the rough surface. In such a case, the Prandtl layer begins from the surface itself. So generally, the lowest layer is referred as surface layer, as laminar sublayer is thin or absent. In the Prandtl layer, turbulent drag force dominates over the molecular viscosity for the exchange process. The thickness of Prandtl layer varies from 50 meter to 100 meter. In this layer, turbulent drag force is one order larger than the pressure gradient force and Coriolis force. Generally, top of surface layer is treated as the height at which eddy stress is 1/10 of the surface eddy stress. The features of laminar sublayer can be explained on the basis of Newton's law of viscosity. Accordingly, we get F by A is equal to tau is equal to mu into dou V by dou X. So here mu is the dynamic coefficient of viscosity. So the tau is the stress applied or force per unit area. The fluid between, suppose a fluid is kept between two plates and upper plate is allowed to move with a uniform velocity v. The fluid between the two plates move along the direction of motion of the upper plate with a velocity v next to the upper plate and zero speed next to the lower plate. In the steady state, the variation of speed with height is linear, so that the force is proportional to the derivative of velocity with respect to z. Thus, we get the molecular stress tau is equal to mu into dou V by dou Z. In the above case, successive layers of fluid have average horizontal speed of translation. Because of the random motion of the discrete molecules, an exchange of fluid particles takes place between one layer and the next. The exchanged particles carry with them the lateral momentum of the original layers, causing an exchange of momentum between layers. From Newton's second law of motion, such change of momentum with time corresponds to a force. Thus, the adjacent layers of fluid exert tangential force upon each other and the stress is transmitted through the fluid. Next, let us consider the situation in which the transition of laminar flow into turbulent flow. If the upper plate speed is gradually increased at a certain speed, the flow pattern changes from laminar to turbulent. This occurs when Reynolds number exceeds certain critical value. When the flow becomes turbulent, the force required to keep the upper plate increases suddenly and the momentum is transferred across the flow, mostly by eddies. Since large scale eddy exchange of momentum is more efficient process compared to molecular exchange of momentum, the stress required increases several times. And we can modify the equation for exchange of momentum. Tau is equal to mu suffix E dou V by dou Z, where mu is the coefficient of eddy viscosity. In the turbulent flow, eddies of all sizes are formed. Kinetic energy is transferred between eddies of different sizes. Next, let us briefly discuss Prandtl mixing length principle. In laminar flow, momentum exchange takes place through random component of molecular motion between adjacent layers of fluid. Prandtl treated the case of turbulent momentum exchange by setting up a reasonable analogy between motion of molecules and the motion of turbulent fluid. Consider a case of turbulent flow with mean motion in the x direction and speed increases, that is dou u by dou z greater than 0. Prandtl assumed that when a parcel of fluid is moved from its original level by turbulence, it carries the mean momentum with it in the x direction of that level. After moving a vertical distance L prime will produce a turbulent fluctuation U prime and will be absorbed immediately by the fluid at that height. Thus, an exchange of momentum between layers will take place by eddy transport of momentum similar to that of molecular transport. If an air parcel originates at the level z plus delta z with a mean speed of u z plus delta z and moves downward to the level z where the mean speed is u z, the perturbation or fluctuation u prime is equal to u z plus delta z minus u z, that is departure from the mean. When delta z is small, u prime is equal to delta z multiplied by dou u bar by dou z, and the displacement L prime can be written as minus delta z. Thus, we can write u prime is equal to minus L prime dou u bar by dou z. That is, eddy stress tau suffix zx is equal to minus rho u prime w prime averaged over time delta t is equal to minus rho w prime L prime averaged over time delta t multiplied by dou u bar by dou z. And mass continuity suggests that horizontal and vertical eddy speeds are equal, so that absolute value of w prime is equal to absolute value of u prime. When a fluid mass is transported to another level, an equivalent mass on an average moves away horizontally with the same speed to make room. Therefore, w prime is equal to L prime multiplied by absolute value of dou u bar by dou z, where absolute is used because W prime and L prime must have the same sign. Therefore, tau Zx is equal to rho L prime square average rho time delta t multiplied by absolute value of dou u bar by dou z multiplied by dou u bar by dou z. A root mean square mixing length is defined as L suffix x is equal to square root of L prime square, so that tau Z is equal to rho Lx square multiplied by absolute value dou u bar by dou z multiplied by dou u bar by dou z. For the surface layer, a constant eddy stress tau 0 is considered and is equal to rho Lx square multiplied by absolute value dou u bar by dou z multiplied by dou u bar by dou z. On the basis of this eddy stress value in the surface layer, let us discuss how the horizontal wind in the surface layer varies, and let us derive an equation for the variation of horizontal wind in the surface layer. The variation of horizontal wind in the surface layer, that is from Z0 to top of surface bound layer or surface layer, the average value can be treated as 80 meter, and the surface layer varies from 50 meter to 100 meter, is popularly known as logarithmic wind profile. And from this, we can evaluate the horizontal wind at any desired level in the vertical in the surface layer. In the surface layer, the eddy stress tau prime Zx is treated as a constant. Let the eddy stress at the surface be tau 0. The level at which eddy stress is 1/10 of eddy stress at the surface. To derive the variation of horizontal wind in the vertical, let us orient the x-axis parallel to the eddy stress for simplicity. So tau 0 is equal to rho Ls square multiplied by absolute value of dou u bar by dou z multiplied by dou u bar by dou z, that is rho into Lx in bracket Lx dou u bar by dou z whole square. That is tau 0 by rho is equal to Lx dou u by dou z whole square, that is Lx dou u bar by dou z is equal to square root of tau 0 by rho, that is dou u bar by dou z is equal to 1 divided by Lx in square root of tau 0 by rho, where rho is the density of air and tau 0 is the constant value of eddy stress in the surface layer and are constant within the given surface layer. The only quantity on the right hand side of the above equation which can vary is L suffix x, root mean square length. The constant quantity square root of tau 0 by rho is equal to u star, which has dimension of velocity and is called frictional velocity. Frictional velocity value depends on the frictional elements in the given surface layer, and frictional velocity u star is equal to square root of tau 0 divided by rho. Thus, the governing equation becomes dou u bar by dou z is equal to u star divided by Lx. And one cannot integrate the above equation to obtain the wind profile in the surface layer until we specify how Lx varies with height. Next, let us see how do we describe the variation of Lx with height. Very near the Earth's surface, mixing cannot take place over large distances because of solid boundary interfaces. As we consider points higher in the surface layer, the turbulence is less inhibited by the solid boundary of Earth's surface. Thus, it is reasonable to assume that the eddies can larger in size at a higher altitude. Hence, to solve the above equation, we assume that the mixing length varies with height above the air surface. That is L suffix x proportional to height z. That is L x is equal to k z, where k is von Karman's constant, a dimensionless quantity. Small letter k is equal to 0.38 as per the initial experiments. Nowadays, von Karman's constant is treated as 0.39 or 0.4 according to different terrain features. Let us apply this in the above equation. Dou u bar by dou z is equal to u star divided by k z. Integrating with respect to z, we get u bar is equal to u star divided by k ln z plus constant. Next, let us evaluate the constant of integration. Over a very smooth surface, u bar becomes 0. But for rough surface, the wind vanishes above the surface. Therefore, we shall apply the condition that u bar is equal to 0 at z is equal to z naught, where z naught depends on the roughness of the surface. Z naught is called roughness parameter. Applying the condition, we can evaluate the constant. Thus, we get the u bar is equal to 0 at z naught is equal to, z is equal to z naught. That is 0 is equal to u star divided by k ln z naught plus constant. Thus, this constant is equal to minus u star divided by k ln z naught. That is u bar is equal to u star by k ln z minus u star by k ln z naught. Combining, we get u bar is equal to u star by k ln z by z naught. Here u star is the frictional velocity, smaller k is von Karman's constant, and nowadays over the topical region, most appropriate value for von Karman's constant is 0.4, and z naught is the roughness parameter. This roughness parameter also depends on the frictional elements in the given surface layer. Actually, the above equation deals with the variation of horizontal wind with height in the neutral surface layer. The roughness parameter z naught can be evaluated with the help of a diagram as shown here, in which y-axis is logarithm scale in z and x-axis is linear scale in u. The equation can be fitted with actual wind data in neutral condition. Here, the velocity values are indicated at different heights against u bar in the x-axis, and a straight line is fitted, and y-intercept in the y-axis gives roughness parameter z naught. It is possible to draw a straight line passing through almost all the points as shown in this diagram. Accordingly, we can evaluate the roughness parameter z naught. Once the roughness parameter is evaluated, we can find out the frictional velocity for the given layer, given surface layer u star, and the logarithmic wind profile for the given surface layer. Thus, the variation of horizontal wind in the given surface layer can be evaluated. Next, let us discuss features of next layer, that is the layer just above the surface layer. The layer just above the surface layer is known as Ekman layer or surface layer, and is generally between 80 meter and top is around 1.5 kilometer. And as I mentioned earlier, depending upon the roughness parameter at the surface, the PBL height varies from 500 meter to 3 kilometer. In an early morning over the ocean surface, the planetary bound layer height is as low as half kilometer. On the other hand, during the afternoon over a complex terrain, we can expect the planetary bound layer height is up to 3.5 kilometer or above. And generally, above the planetary bound layer, the frictional force is small, and hence we can consider the air as free air balancing the pressure gradient force and geostrophic force to have geostrophic wind. The spiral layer or Ekman layer is a layer in the PBL in which pressure gradient force, Coriolis force, and turbulent drag force are in the same order of magnitude. It is considered that in the spiral layer, these three forces are in balance, but the turbulent eddy force due to surface friction decreases with altitude. The spiral layer extends from top of the surface layer and is up to the level at which the effect of surface friction is negligibly small. The top of spiral layer is also top of the PBL and is called gradient wind level. At this level, the flows are in general parallel to isobars. Since wind in the spiral layer is generated as the balance of three forces and turbulent eddy stress force decreases with altitude, the cross isobaric angle decreases in the spiral layer and approaches to zero at the top of planetary bound layer. On an average, near the surface, the cross isobaric angle is around 15 degree and it becomes almost zero at the top of planetary bound layer because of negligibly small frictional force at the top of planetary bound layer. So the winds are isobaric above the gradient wind level. Thus the actual wind turns clockwise in the northern hemisphere with height in the planetary bound layer. Next, let us discuss how to obtain an equation for the horizontal wind at different levels in the spiral layer and is known as Ekman spiral solution. For this, we consider the momentum equation in the Cartesian coordinate system. We know du by dt is equal to pressure gradient force, Coriolis force, and frictional force. Similarly, y component momentum equation. Since its temporal scale of turbulent motion is very small compared to the rotation of the Earth, the Coriolis force terms can be neglected for the derivation of Ekman spiral solution. In the spiral layer, turbulent eddy force is large compared to molecular viscosity, and hence the effect of molecular viscosity in the spiral layer can be neglected. We have already derived the equation for mean motion for turbulent flow in the y direction as given below. I am sorry, I do not show the steps for equation for mean motion for turbulent flow. It is dv by dt is the y component of equation for turbulent flow. Equation for mean motion for turbulent flow in the y direction is dv by dt is equal to minus 1 by rho dou p by dou y minus f u bar plus 1 by rho in double bracket dou by dou x of minus rho u prime v prime etc. And the turbulent drag forces in the x and y directions are small in the spiral layer in comparison with that in the z direction, and hence the horizontal components of turbulent drag forces can be neglected. So we consider the turbulent drag force in the z direction 1 by rho dou by dou z of minus rho v prime w prime. Here minus rho v prime w prime is tau prime zy called Reynolds stress or eddy stress. Thus, the equation for mean motion for turbulent flow can be expressed as dv by dt is equal to minus 1 by rho dou p bar by dou y minus fu plus 1 by rho dou tau zy by dou z prime. This prime is used to indicate eddy stress. In the spiral layer, we consider turbulent eddy stress force as it is dominant over molecular viscosity, and hereafter we do not use the prime for convenience. Since pressure gradient force, Coriolis force, and turbulent eddy stress force are in balance in the spiral layer, LHS can be treated as zero. Because these three forces are in balance, there is no unbalanced force to indicate in the LHS. Thus, the equation of mean motion for turbulent flow in the horizontal directions x and y can be written as 0 is equal to minus 1 by rho dou p bar by dou x plus vf v bar plus 1 by rho dou tau z by dou z in the x direction, and 0 is equal to minus 1 by rho dou p bar by dou y minus f u bar plus 1 by rho dou tau y by dou z in the y direction, and they can be combined by multiplying the second equation by unit vector I, multiplied by simply I, where I is equal to square root of minus 1. It is simply I is equal to square root of minus 1. And adding, we get the standard procedure for combining equations in the two directions is adding with the second equation multiplying by simply I, where I is equal to square root of minus 1. So we get an equation as shown in the display. And now let us combine similar terms. The equation becomes 0 is equal to minus in bracket dou p by dou x plus I into dou p by dou y close the bracket plus rho f in bracket f minus iu close the bracket plus dou by dou z of in bracket tau zx plus I tau zy. From Newton's law of viscosity and Prandtl's mixing length principle, tau is equal to mu into dou u by dou z is equal to rho k dou u by dou z. That is, tau zx is equal to rho k dou u by dou z, and tau zy is equal to rho k dou v by dou z. Combining, we get tau zx plus I tau zy is equal to rho k in bracket dou u by dou z plus I dou v by dou z. Again, combining similar terms together, we get the equation as shown in the display. In order to derive the Ekman spiral solution, it is easier for us to solve the governing equation by assuming certain points such as 1. The horizontal mean motion exists. There is no vertical motion, so that W is equal to 0. Second assumption is dou t by dou x and dou t by dou y are small. Let me say dou tau by dou x and dou tau by dou y are small compared to dou tau by dou z. Isobars are oriented parallel to x-axis, so that dou p by dou x is equal to 0. And balance of pressure gradient force, Coriolis force, and turbulent drag force takes place at each level. I repeat, the third assumption is isobars are oriented parallel to x-axis, that is dou P by dou S is equal to 0, and balance of pressure gradient force, Coriolis force, and turbulent drag force at each level takes place. And fourth assumption is existence of an eddy diffusivity coefficient, that is K is equal to mu by rho, which is independent of altitude. Fifth assumption is dou P by dou Y and density rho are constant throughout the spiral layer. Since isobars are oriented parallel to x-axis, x component of geostrophy wind x is and y component of geostrophy wind v suffix g is equal to 0. That is ug is equal to minus 1 by rho f dou P by dou Y. That is dou P by dou Y is equal to minus rho f ug, and dou P by dou x is equal to 0 because isobars are parallel to x-axis. Therefore, the combined equation becomes as shown in the display. After simplification, we can write 0 is equal to I rho f ug minus rho f I in bracket u plus iv close the bracket plus rho capital K dou squared by dou z square in bracket u plus iv. As per the assumption, the pressure gradient does not vary with height. We can simplify the governing equation so that dou by dou z of dou P by dou Y is equal to 0. That is dou by dou z of minus 1 by rho f dou P by dou z is equal to 0. That is dou by dou z of ug is equal to 0. That is ug is a constant in the given bound layer. That is dou square by dou z square of ug is also 0. Applying in the given context and dividing each term of the combined equation by rho and k, the equation becomes as shown in the display. And by simplifying further, we get I multiplied by f divided by capital K multiplied by in bracket u plus iv minus u suffix g close the bracket minus dou square by dou z square multiplied by again the same variable u plus iv minus ug close the bracket is equal to 0. We can replace the partial differential equation dou square by dou z square of u plus iv minus ug by ordinary differential equation, since z is the only independent variable. So the above equation becomes I multiplied by f divided by capital K in bracket u plus iv minus ug close the bracket minus d square divided by d z square multiplied by u plus iv minus ug is equal to 0. The above equation is a second order homogeneous linear differential equation with constant coefficients. The thickness of Ekman layer is far greater than surface layer, and hence we can ignore the surface layer and assume that the wind vanishes exactly at the earth surface, that is z is equal to 0, and approaches ug at the top of planetary bound layer. The vertical distribution of the independent variable u plus iv minus ug can be determined by applying the above boundary condition, that is at z is equal to 0, u plus iv is equal to 0, and at z is equal to infinity, u plus iv is equal to ug. The above differential equation is in the standard form and its solution is u plus iv minus ug is equal to capital A multiplied by e raised to square root of if divided by capital K multiplied by z plus b multiplied by e raised to minus square root of if divided by capital K multiplied by z, where a and b are two arbitrary constants to be determined by the first boundary condition, that is z is equal to 0. We get minus ug is equal to a e raised to 0 plus b e raised to 0, that is a plus b is equal to minus ug, and a e raised to infinity is equal to 0, so that a is equal to 0 and a plus b is equal to minus ug, so b is equal to minus ug. By the second boundary condition, u plus iv minus ug is equal to minus ug e raised minus e raised to minus square root of if divided by k z, that is u plus iv is equal to ug into 1 plus e raised to minus square root of if divided by k z, and by simplifying we get u plus iv is equal to ug multiplied by in bracket 1 minus e raised to minus az, again multiplied by e raised to minus iaz. For simplification, I just considered e raised to minus infinity is equal to 0, everybody knows, and I is equal to square root of minus 1, we assume like that, and 1 plus I square is equal to a plus b square is equal to a square plus 2ab plus b square. In this particular context, it is equal to 2i. So 1 plus I is equal to square root of 2i, that is square root of 2 square root of I. Therefore, square root of I is equal to 1 plus I divided by root 2. This is applied for simplification, and finally we get u plus iv is equal to ug multiplied by in double bracket 1 minus e raised to minus az in bracket cos az minus I cos I sin az, close the bracket, close the double bracket, equating the real and imaginary parts to separate the solution for x component of and y components of wind. We get u is equal to ug multiplied by 1 minus e raised to minus az cosine az, close the bracket, and y component of wind small letter v is equal to ug multiplied by e raised to minus az sin az. This is classical Ekman spiral solution. U and v at any height in the spiral layer can be evaluated using the above equation, and this is known as Ekman spiral solution. So these two equations provide us the horizontal wind components at different levels in the spiral layer. As per the assumption z is equal to 0, v becomes 0, correspond to ground. Next level at which v is equal to 0 is as z is equal to pi, so that sin pi is equal to 0, that is sin 180 is equal to 0. So at z is equal to pi by a, that is v is equal to ug e raised to minus az sin pi. Y component of actual wind vanishes and the flow becomes ug. Thus, u is approximately equal to UG multiplied by 1 plus 0.1 after simplifying the equation at Z is equal to pi by A. The ratio V to U is the tangent of the angle and wind makes with the eastward direction, or the wind makes with the isobars. And at Z is equal to 0 and the components U and V are 0, then tan alpha C is equal to 0 by 0, where alpha C is the cross isobaric angle. This is indeterminate form, and this can be evaluated by differentiating numerator and denominator separately with respect to Z and examine the ratio of derivatives as per L'Hospital's rule, so that we can obtain the cross isobaric angle alpha C at the surface as 45 degree as per the classical solution. That's all. By this, I stop the lecture on features of planetary bound layer and the variation of horizontal wind in the surface layer and in the spiral layer. I invite a few questions. Mic is given to the organizers.
Hello.
Yes.
Sir, okay. So we will take the questions after the photo session.
Yeah. Do
So
you have
please,
anything else to be done by me immediately?
no.
Okay. Okay.
So
Because
we
time
will,
is over, and now time is 3:52. I think I exceeded about 7 minutes.
sir, it is fine. No problem.
And since it involves a lot of equations and the steps are to be explained properly for understanding, I took more time than expected.
Okay. So just we will take we will take photo and then we will continue with the question answer session.
Yeah, okay.
So I request everyone to please switch on their cameras. Tyagi sir, Professor Babu sir's camera is not
I'm
working.
sorry.
Yeah,
Today my
today it's not
camera is not working. Sorry.
Dr. Swagata, Dr. Divya, Tyagi sir. Ashwin, can you take one? Yeah, Dr. Swagata is also here. Yeah, now you can take. Okay. So now I request Dr. Divya Prakash to please moderate the question answer session.
Okay, thank you, ma'am. So, yeah, sir, there is one question. Sir, do you think the wind profile can be exactly as per the equations derived in the PBL, or any deviation are observed?
Actually, the equations are based on many assumptions, and in the real situation, the actual flow pattern need not be as per the equation. There can be minor variation 2 to 10%. I hope the answer is clear. And further sub question, I am ready to explain further. On the basis of sub question, I am ready to elaborate further.
Okay, thank you, sir. Ma'am, Rohini ma'am, is there any other question?
Yeah, there is one more. What is the correlation between wind speed and rain occurrence?
Wind speed and
Rain occurrence.
And there is no such correlation because rain occurrence depends on the cloud development and subsequent situation for the rain processes. It is nothing to do with the features in the bound layer, and hence it is difficult to have a relation between bound layer features and rain processes.
Yes, sir. Thank you.
Welcome.
At present, I think Dr. Divya, there are no
Yeah,
more
ma'am.
questions.
Yeah, there is no question is visible. So thank you, ma'am. Thank you,
Yeah.
sir.
Yeah, thank you for listening me and interacting with the two questions. And further questions can be answered via email. I will share the PDF with the email ID, and those who are interested can go through and interact me via email. I will try to answer the questions within 24 hours. Thank you.
Yes, sir. So
Thank you, sir. Thank you.
before we go to the vote of thanks, I would like to give some few announcements. On 26th of July, we will be having the exams. So a detailed email will be shared on 21st regarding the exams. Also, the link will also be shared, which will be activated only on 26th. The time will be the same from 3 to 5 o'clock, whatever we have the same time. So participants, please, also the link was shared for the study material. So please go through the study material, also the lectures on YouTube for giving the exams. Anything else, sir, we have to tell them? Dr. Swagata, anything else?
No, there are different type of certificate will be provided.
Okay. Attendance certificate, participation certificate, and grade certificate, those who give exams, of course. So we are in the process of checking the attendance of the participants. We already, in the first few lectures, we have mentioned multiple times that 75, those who have 75% and above, they will be share, the link will be shared with them. So definitely we'll be sharing the link. So we are in the process of that. You will be getting the email. If you have any questions regarding that, please write email to the email ID from where you get the poster. So, or in the common WhatsApp group. I request now Mr. Ashwin Zadav from SPPU Pune to please give vote of thanks.
So I think there would be one more announcement after 21st. Rainy, just I wanted to convey one more thing.
Yes.
That if someone has not reached, if someone has not
Dr. Swagata, again. No, again. Your network,
someone has
you are
not
not
received the email. 21st.
Not audible, sir. You are not
not
audible.
audible. Yeah, not
Okay.
audible. We will be sharing the exam related details on different dates like 21st, 23, 25th. So in the week, we will share the email to all the participants thrice. So everyone, also we will share the same email in the WhatsApp group, the common WhatsApp group, which was created for the participants. So I think Dr. Swagata wants to say that if anybody has not received any email regarding the exam link, please contact on the same email ID, atmospheric dynamics 2025 @gmail.com. So please, Ashwin.
Yes, ma'am. Thank you, ma'am.
I have one small doubt. I am CA Babu. I have one small doubt.
Yes, sir.
And do you expect any support from the speakers or lectures regarding setting up question paper for the test? I do not remember you sent mails, but I could not remember.
Sir, we need multiple choice questions, 5 to 7 from each lecture of yours.
Each lecture, okay. And before which date?
Sir, as soon as possible.
Okay. 5 to 7 multiple choice objective type questions and no
Yes.
short answer, no essay type questions.
No, only multiple
And
choice.
no numerical problems.
No, sir. Yes.
Okay. Thank you.
Okay, sir. Yeah, Ashwin.
Yeah, sure, ma'am. On behalf of our organizing committee, I extend my sincere thanks to everyone who contributed to the success of the 25th lecture in our weekly online lecture series on atmospheric dynamics and its application to climate sciences. We are especially grateful to Professor Ajit Tyagi, President SAMA, for his welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Professor C.A. Babu, for delivering an enlightening lecture on mixing length theory, vertical profile of mean horizontal mean Ekman layer in viscous sublayer. I would like to acknowledge Dr. Rohini Bhar for moderating the session and Dr. Divya Prakash for efficiently managing the question answer segment. Additionally, I appreciate the guidance and support of all the panelists and EC members. A special thanks to all the participants and attendees who joined us from the globe and the dedicated team members at Savitribai Phule Pune University for their valuable role in organizing this lecture. Thank you all.
Yeah, thank you, Ashwin. So the participants are asking questions like right now I saw in the Q&A box, I haven't received any exam link. No, you will not receive during this week. You will receive the exam link only next week and it will be only activated on 26th of July 2025 at 3 p.m. So please keep a watch in your email box. For today's statistics, 80 participants have registered their attendance, out of which 68 participants have rated it as excellent or very good. So thank you, Babu sir. Now I request Professor Someshwar Das sir to say few concluding lines. Sir, you are muted.
Oh, I see. Okay. Thank you very much, Dr. Rohini. I hope I'm clearly audible.
Yes, sir.
Well, today, as you all know, is the concluding lecture of the longest lecture series that has been conducted by SAMA. And thanks to Dr. Rohini and her team from the Savitribai Phule Pune University for doing this great job of conducting lecture for more than 6.5 months, almost 25 lectures. That means more than 6.5 months. And as most of you who have been regular, you might remember that we started this lecture series on 18th of January, and today is 19th of July. So we have concluded a long journey of a very tough, challenging, and interesting subject on atmospheric dynamics. As many of you may know that this subject is one of the core subject of atmospheric science, the fundamentals like the atmospheric physics and atmospheric dynamics, the two, in fact, govern the whole motion of the atmosphere that create everything that you see in the sky, whether it is a day-to-day changes in the weather or the long-term changes in the climate. So fundamental of all that is the physics and dynamics of the atmosphere, the science behind that. All other things are like applications or maybe the observations, the measurements. You have also heard, maybe some of you might have attended our earlier lectures on the two very important topics on the satellite meteorology that was conducted jointly by SAMA and the BIT MESRA, and also the radar meteorology that was conducted by SAMA and the ACAR, the Atmospheric Advanced Center for Atmospheric Radar Research of Cochin University of Science and Technology. So far, we have conducted 5 lecture series, and all of them are very, very important for the fundamental knowledge of atmospheric science. If you want to do real good research, then these subjects are very important. I know many of you might not have understood everything that has been told in this online classes, but as we have been saying that all the lectures, past lectures are also available on the YouTube channel of SAMA of this lecture series as well as of the past lecture series. So those who are really interested, they can always go back to the YouTube and watch the lectures. It is useful not only now but also in the future, because some of you might know that we are planning that, like as already been said, that certificates will be provided. There will be three types of certificates. One will be just the participation certificate, other will be the attendance certificate. Those who have attended more than 75% of the lectures live, by the way. I'm not sure how many are really real attendance and how many are just the fake attendance, because the attendance are marked like more than 80%, 80 people, but we see hardly 50 people, 55 people logged in. So maybe I do not know whether some of the attendance are just fake. But in any case, the people or the participants who have attended more than 75% of the lectures, they will be given the attendance certificates, and most importantly, those who will appear in the examination. Somebody was asking whether that will be the only examination. Yes, that will be the only final examination for this lecture series that we are planning to conduct on 26th of this month. And as you know, this will be a multiple choice question type of examination for 1 hour. And based on your score, you will also be given the grade certificates like outstanding, excellent, very good, good, etc. And by the way, we are making the Google form for your feedback, so that will be shortly shared by Dr. Rohini to all the participants. So you can give your feedback about this lecture series, how you felt it. Now, whether you could understand, or there was a lot of difficulties, etc., or you would like to suggest something for improvement of this in the future. Those things you can fill up in the feedback. We have got very good feedback for our past lecture series, in which many participants, not only, I mean, they gave feedback online, but some of them whom we met physically at different conferences, they walked in personally to tell us, or thank us for the lecture series that we conducted in the past, saying that, sir, it was very, very useful. And they were, I mean, meeting me for the first time. They had never met me before. And then they were profusely thanking for this lecture series, because they said that based upon the certificates that they received after attending this lecture series, they got a lot of benefits. Like some of them got a promotion in the project, from PRF to SRF. Some of them got a hike in the salary, etc., etc. So very good feedback. For those who are really keen and serious and interested to learn the subject, they will definitely get benefited. And we are also planning, I will just, for the sake of information, that even for the past lecture series, after the end of every lecture series, we have given the certificates based on their performance in the examination. But now, those of you who have missed the past lecture series and yet you want a certificate of that, probably in the future we are planning that we shall conduct like in a periodic examination for each of those lecture series, and maybe in the future you will have to pay for the certificates to get a certificate, like to appear in the examination. You'll have to maybe pay the examination fee, and then appear in the test, which will be conducted now periodically. And then depending upon your, again, score, you will get the certificates for that. So a lot of things are in the pipeline. And after this lecture series, again, after a gap of maybe few weeks or maybe 1 or 2 months, we shall start another course, likely on WRF, urban WRF modeling. A lot of development, research articles, research papers are getting published on the urban WRF, which is direct applications of the modeling on the real time on different cities. Like you might have heard about the urban heat lines, and many more things, like why some city gets flooded, some city does not get flooded, why there is strong rainfalls somewhere, why there is dry weather at some other places like that. So all these things, and also related to the quality of the air quality, etc. Well, maybe in future we shall also conduct a similar lecture series on the air quality, air pollution, etc. But no, that will be in the future. But in any case, this is about the lecture series. And by the way, some of you who are the members of SAMA, either life member or the student member, you all may be knowing that SAMA was established on 3rd of August. And so every year we celebrate our Foundation Day on 3rd of August. And this year also, after 2 weeks, we shall celebrate the Foundation Day of SAMA on 3rd of August. So those who are the members, they will get anyway information about that. Those who are not members are requested to join SAMA either as a life member or as a student member, so that you will keep getting benefited by the activities of SAMA, and also you will keep getting benefited by the lecture series that we have conducted in the past, as well as in the future. Okay, so all of you, I mean, maybe we have got the database of all the participants who may or may not be the members of SAMA. But Rohini, we can send the mails to all of the participants who have registered for this course. Also, as you know, more than 1150 people registered for this course, and many of them are already members of SAMA. Some of them may not be members, but we can circulate email, Zoom link to all, so that you can all attend the Foundation Day ceremony. And also, all of you are urged to join join SAMA as a life member or student member, depending upon your status. So with this, well, Dr. Tyagi Saab has now come. Maybe we can have once again the photo session. Dr.
Yes,
Rohini,
sir.
because
Yes, sir.
we missed
Yes.
last time. Yeah. So thank you very much, Dr. Rohini. Thank you so much.
Thank you, sir. Yes, we will definitely be sharing the Foundation Day link to all these members also, sir. So I
Yes.
request everyone to please switch on their cameras again. We would take one more picture. Ashwin?
So many more, right?
Yes.
Yeah, Professor Babu's camera is not working anyway, so we'll miss him.
I'm sorry.
Yeah,
Due
but
to
anyway,
the
thank you so
complaint
much.
on my camera, I am unable to show camera.
We can do
problem, no
Photoshop. We can do a Photoshop with Babu Saab.
Last, yes.
Right, right.
That is very much required.
Okay.
Yeah.
So I request all the participants to keep a watch on their email box, inbox, whatever it is, for the detailed mail. We will be putting all the details regarding the exams, how it will be conducted, what it will be, what will be the time, everything in the mail. So,
Yeah.
Sir, Tyagi sir, any
No,
concluding?
compliments and thanks to you and your team, and also for Professor Babu for supporting SAMA in this lecture series. And we continue to look forward for more association with Professor Babu, such a positive and dynamic, I think, academician. So thank you so much, Professor Babu, and of course, Rohini and our team. Great. We should follow it up, wide publicity to our YouTube lectures so that more students can benefit. And also, we should send, I'm sure you must be planning to send letter of thanks to all our esteemed faculty who have delivered the lectures. This is very important to acknowledge their contribution.
Yes, sir. Yes.
Oh, thank you. Thank you, Rohini.
Sir. Yeah, thank you, sir. I will stop live streaming first.